Today, what I'll do is I'll solve one problem for Fourier series and a related question: how to find the sum of a Fourier series at the end point of the given interval. Okay, one sum of that category, and another sum I'll do from Parseval's identity. Okay, so I'll be doing two problems. I think that will be enough for one hour long session solving two problems itself. And I'll hope that everyone remembers the basic formulas for Fourier series and obviously the basic integration formulas also. Okay, so I'll not be brushing through the basic formulas. I'll directly start the questions. Okay. Achha, so before I start, I'll just show you the formulas on the screen. If you don't remember, take a snapshot and remember it. I'll be starting to do problems on that. Okay. So this is the basic formula of Fourier series. I hope everyone knows and remembers this formula. If the interval is minus t to t, then this is the formula for finding out the Fourier series expansion, where t corresponds to the lower limit and the upper limit of the given interval. Okay, a n cos n pi x by t, b n sin n pi x by t under the summation, and a0 by 2, where a0 is 1 upon t minus e to t integration fx dx. An is given by this integration and bn is given by this integration. So this is just basic formula, not going much into details. Just one thing what I'll say is, if instead of t, like this is the most generalized formula, if instead of t, if the interval was minus pi to pi, okay, like which is a more specific case, like a more frequently occurring case. Okay, usually we don't get t. What you might get is, let's say, minus 5 to 5. So in that case your t value becomes 5. But generally we get a question where it is minus pi to pi, okay, more related to pi. So what happens, the formulas become simpler if it is pi. If it is pi, then this will be pi and this will be pi. Then you can see the pi will get cancelled, right, if the t becomes pi. Similarly over here, the range of the integration is going to become from pi minus pi to pi, and again pi and pi will get cancelled, minus pi to pi integration range, and pi will cancel. So this will be the corresponding formula if the range is minus pi to pi. Okay, the problem which I'll do right now, that will have a minus pi to pi range. So that's why I have written the formula explicitly for minus pi to pi. I'll just rearrange that once again. So this is going to be simply nx, the pi is getting cancelled, and this is going to be simply nx, the pi is getting cancelled. So similarly, things over here, the pi is getting cancelled. This is all becoming nx, cos nx, sin nx. So this will be my working formula if the interval is minus pi to pi. Okay. So now I'll start solving one question. Let's say this is the function given, fx equals e to the power x, and as I told you, the range is going to be minus pi to pi, and then I need to find out the sum of the series at the end points of the given interval, right? The interval is minus pi to pi, so I need to find the sum at the end point. Okay, there's a specific formula for finding the last part. Okay, I'll come to that later on. If it is asked that find the sum of the series at the end point of the given interval, there is a specific formula to use. So I'm coming into that later. First, I'll concentrate on finding the Fourier series of the given function. Okay. So first we need to find out a0, and as you have seen, the formula for a0 is 1 upon pi minus pi to pi fx dx. So I'll just use the formula 1 upon pi minus pi to pi fx dx. My fx is e to the power x, so e to the power x dx. So that's just basic integration. So it's going to be e to the power pi upper limit minus lower limit. Okay, so I don't want to keep it this way. Now you might recollect some formula for from trigonometry. I can bring this down to hyperbolic function. Okay, so I'll just multiply 2 in the numerator and 2 in the denominator, and this entire part is going to become sine hyperbolic pi, right? It's a formula for sine hyperbolic pi. If it was a plus over here, then it will be cos hyperbolic pi. If minus, then sine hyperbolic pi. So this is becoming 2 sine hyperbolic pi by pi, and this is my a0 value. Okay, so done with A0. Now I'll try to find out the AN value. AN formula was 1 upon pi minus pi to pi fx cos nx dx, right? Fx is e to the power x cos nx dx. Okay. Now you need to memorize this integration formula, the direct formula for this. I'll write down the formula. If it is e to the power ax cos bx dx, the direct formula was e to the power ax by a square plus b square a cos bx plus b cos bx. Okay, so I will use this direct formula over here. Here my a is 1, e to the power 1 into x. So my a is 1 and my b value is n. Okay. So a is 1, b is n. So a square plus b square, it's going to be a square plus b square is going to be 1 square plus n square, which is 1 plus n square. Okay. So I'm directly using the formula over here. I will get 1 upon pi e to the power ax, which is simply e to the power x, by a square plus b square, which is 1 plus n square, whole common. A cos bx, a is 1, so 1 cos nx, right? So 1 cos nx plus b cos bx, where b is n, so n cos nx, n cos nx, and my limit over here is minus pi to pi. So limit is minus pi to pi. Acha, remember one more thing, in this kind of question, usually whenever you have minus a to a limit, we check whether it is odd function or even function. But here e to the power x is neither odd function nor even function. So that's why we are not checking for that. Okay, usually in these kind of sums, odd even function happens. So if it is odd function, the integral becomes 0. If it is even function, we change the limit accordingly. But here nothing like that is happening. So we are not changing anything. Okay. Acha. So I'll put the limits directly. 1 by pi. If I put the upper limit is pi. So e to the power pi. Acha, I'll bring the 1 plus n square outside. Like 1 plus n square is a constant. So I'll bring that outside. 1 plus n square. And if I put pi now, so pi in place of x, I'll have e to the power pi. Pi in this place, I'll have cos in pi. And pi over here I'll have plus n. Acha, one second. I think I have written the formula a little bit wrong. Sorry. This should be sin x. Sorry, this should be sin x. A cos bx, b sin a cos bx, b sin bx. Okay, I've written formula a little bit wrong. So this should be sin nx. Okay. So if I put pi in place of x over here, pi in place of x, sine n pi, and we know sine n pi value is 0. Okay, sine n pi value is 0 and cos n pi value is minus 1 to the power n. So these two things will be used every time they appear. Okay, so if I put pi over here, it's becoming 0. So I'm not writing it. I will close the bracket. So this is the upper limit I've put, minus, now putting the lower limit, e to the power minus pi cos of n pi. So if I put minus pi in cos, minus gets absorbed in the cos. So simply I will have cos n pi minus getting absorbed. So cos n pi. If I put the lower limit in place of sine, again sine n pi, it becomes 0. So again, not writing the other part, it's becoming 0. Okay, so I can take a cos n pi common, and the value of cos n pi is minus 1 to the power n. I can put that also. So taking cos n pi common, minus 1 to the power n by pi 1 plus n square, and I am having e to the power pi minus e to the power minus pi. which is again going to that sine hyperbolic formula. Just one 2 is required. So I will multiply one 2 outside and inside. Then this part goes to sine hyperbolic. So I get 2 minus 1 to the power n by pi into 1 plus n square sine hyperbolic pi. So this is my value for an. Okay, so I've got my a0 value, I've got my an value. Similarly, I need to find out the bn value. Okay, acha, I'm not checking the comments please right now. I'm just concentrating on the sum. So whatever you're writing, I'm not seeing right now. Okay, so now I will go to finding the bn part. Bn, the formula was 1 upon pi minus pi to pi, and the formula was over here. Bn was fx sine nx dx, right? Fx sine nx dx. So I'll just put that over here. Fx is e to the power x sine nx dx. So again, I need to use a direct formula over here, just like the previous case. So I'll write the formula. If I have e to the power ax sine bx dx, the formula is e to the power ax by a square plus b square. The starting part is same like the previous formula. Just the inside part will be a little bit different. You will have a sine bx. In case of sine, the symbol is minus, not plus. So minus b cos bx. So again, this formula needs to be remembered, and we will apply the formula right over here. So if I apply the formula, I will be getting 1 upon pi. E to the power ax is simply e to the power x by a square plus b square is again the same. A is 1, b is n. So a square plus b square is 1 plus n square, just like before. So it's 1 plus n square. And in the bracket, I will have a sine bx. A value is 1. So 1 sine nx. That means simply sine nx minus b cos bx. B value is n. So n cos nx. So minus n cos nx. And the entire limit from minus pi to pi. Okay, so I'll just bring the 1 plus n square outside. And if I put the limits, putting the upper limit, so if I put the upper limit over here, sine n pi, it's going to become 0. So I'll not write that term. So simply e to the power pi, bracket open, the first term is becoming 0, minus, if I put pi over here, that term remains. So n cos n pi. So this is the upper limit, minus, now putting the lower limit, so e to the power minus pi. Again, if I put this lower limit in place of sine, it's again becoming 0. So 0 minus, if I put minus pi in place of x, in the cos function, the minus sign gets absorbed. So I will simply have cos n pi. Okay, minus getting absorbed. So minus n cos n pi. Okay, and bracket close. So here I can see that I can take n cos n pi common. So I'll bring that common. N cos n pi. I think I can take a minus also common along with that, one minus sign. So I'm taking a minus sign common by pi 1 plus n square. So I've taken minus cos n pi common. I will be having e to the power pi, and over here minus minus it's becoming plus, taking a minus common, so again becoming a minus. And again I can bring this down to sine hyperbolic. So for that I will require 1 2 over here and 1 2 over here. So and cos n pi value is minus 1 to the power n. So minus 2 into minus 1 to the power n by pi into 1 plus n square, and this value is sine hyperbolic pi. So this is my value of bn. Okay, so these are all the required 3 terms that we need to find out. Now we can find the final Fourier series from here. Okay, so now going to the final Fourier series. So therefore the Fourier series, the formula was a0 by 2 summation n1 to infinity an cos nx plus bn sin nx. Now putting all the values of a0, putting the value of a0, an, bn. Okay, putting the values from above. The value of a0 was, this was the value of a0, 2 by pi sine hyperbolic pi. So if I bring the 2 on the left side, if I bring this 2 on the left side, a0 by 2 is simply sine hyperbolic pi by pi. Okay, a0 by 2 is sine hyperbolic pi by pi. So a0 by 2 sine hyperbolic pi by pi plus summation 1 to infinity. Okay, I need the an value. The an value was, this was the an value, 2 times minus 1 to the power n pi into 1 plus n square sine hyperbolic pi. Okay, so I'll put this value, 2 minus 1 to the power n pi 1 plus n square sine hyperbolic pi. Okay, so this was the an value multiplied with cos nx. So multiplied with cos nx. This is just the first term. Now the second term, this is the bn value. Achha, so if I put the bn value, there is a minus sign over here. So minus bn value is 2 times minus 1 to the power n by pi 1 plus n square sine hyperbolic pi multiplied with sin x, sin nx, sin nx. Okay, so let me see what are the things we can take common from here. The terms which are not in terms of n, that means the terms which I can bring outside the summation. I think 2 by pi and sine hyperbolic pi. These are the terms I can take common. 2 by pi, sine hyperbolic pi. These terms I can bring it outside the summation. Okay. So sine hyperbolic pi by pi summation 2 by pi sine hyperbolic pi summation n equals to 1 to infinity. Achha, now inside the summation I can take this term common, right? Inside the summation I have these two terms common, so I'm taking minus 1 to the power n by 1 plus n square common, and what I have is cos nx minus sin nx, cos nx minus sin nx. And this is the entire Fourier series answer. Okay, so this is finding the Fourier series. Now there was another extension part to the question. Okay, so up till here, now if anyone has any questions, please ask. I will pause for a while here and I will go on to the next part. Come on, tell me. Anyone has anything to say? Okay. All right. So continuing from here, there was another extension part. The extension part was, what is the sum of the series for x equals to plus minus pi? That means at the end points of the interval. Okay. Now there is a small formula for this. Let me go through the formula. If suppose the interval is, let's say, minus t to t. Okay, I'm writing the generalized formula. So if in case it is pi, you can change the formula accordingly. If it is minus t to t, and if the question is asking that find the sum at x equals plus minus t. Okay, if this is the question, if I draw a number line, let's say this is minus t, this is t. So we need to take the average of the value of the function just inside minus t and just inside t. Okay. Now how to write something just inside minus t and just inside t? That means the inside portion from both sides. Okay. This is how I will write. I will take the average value. Okay, I will take the average. So I want to go just inside or the just on the right hand side of minus t. If I want to go just on the right hand side of minus t, then with minus t I want to add one h. Okay, I'm adding one h. That means I'm going just on the right side of h where my h value is tending to 0. Okay, so I'm going just on the right side of h. Similarly, I want to come just on the left side of t. Okay, just on the left side of t. So that is going to be f of t minus h. Right, so just on the left side of t is t of minus h. I want to take the average of these two, so I will add them and divide it by 2. Okay, so whatever the answer this will give, that is the sum of the series at plus minus t. Okay, so this is the working formula. Just on the right side of minus t and just on the left side of minus t, the two function value average where h tending to 0. Okay, so I will use this formula over here in this question. So in this question I have minus pi to pi instead of minus t to t. Okay, so if the interval is minus pi to pi, then over here instead of t I will have pi. Okay, just instead of t I will have pi. Acha. All right, so I'll just put the values here. Limit h tending to 0. Achha, f of minus pi plus h. My function is e to the power x. Okay, my function is e to the power x. Here I have to put function of minus pi plus h. That means e to the power minus pi plus h. Similarly, this function is going to be e to the power pi minus h by 2, where h tending to 0. So now if I put h tending to 0, simply that means if I put h value 0, I will have e to the power minus pi plus e to the power pi by 2. And this is the formula for cos hyperbolic. So this is cos hyperbolic pi. So this is the sum of the Fourier series at the particular end point plus minus pi. Okay, so that is the answer. And this is the way of doing it. Okay. So this is one sum. One more problem I'll do, which is on Parseval's identity. Okay. Before that, let me walk through the formula. I'll do one Parseval's on a half-range Fourier series. Okay, half-range Fourier, Parseval of that. So half-range, this was the formula that if you have a half-range sine series, if it is half-range sine series, then this is the Fourier series. We only take the sine part, the cos part is not there. Similarly, if you want half range of cosine series, the a part or the part associated with cos, that part is there, the sine part is not there. Okay, so this is the Fourier series for half range cosine. And the change in the formula was, there was just one change, that one 2 is multiplied and the interval is 0 to t, not minus t to t. Previously it was 1 upon t minus t to t. Now it is 2 by t, 0 to t. Half of the interval multiplied with one 2. Similarly, half of the interval 0 to t multiplied with one 2. Okay, and similarly for an, 0 to t multiplied with one 2. So this is the only change when we are doing a half range, whether it is sine or it is cos. And for Parseval's, the formula was, if it is a normal like sine cos Fourier series involving both the terms, then this was the identity of Parseval's, that 1 upon t minus t to t, the whole square of the function, integration of the whole square of the function. The coefficients are going to be there. The sine cos is not there. The whole square of the coefficients are going to be present. A0 square by 2, an square, bn square. The sine cos part is not there. So if now I have to do Parseval's for a half range, let's say I have to do Parseval's for a half range sine. Okay, for a half range sine series. So if I punch the two things, that means I have to punch the half range sine this formula with the Parseval formula. The moment it is half range, the interval is going to become 0 to t, not minus t to t. The interval will automatically change to 0 to t. Okay, so here the limit will be 0 to t. Okay, 0 to t. As I told you, in half range what happens, one 2 is getting multiplied, so there will be one 2 multiplied over here, 2 by t, 0 to t, fx whole square dx. If I take sine series, for sine series, what are the terms present? For sine series, only the bn term is present, an term is not there. For sine, only bn term is there. So that means this an term will be not there, this an term will be not there. So this will be the Parseval's identity for half range sine. Similarly, if it is half range cos, then left hand side is same. In the right side, the bn term will be not there, only the a0 and the an term will be there if it is half range cos. So right now I want to deal with the half range sine. So this a0 square will be absent, this an square will be absent. I only have to find out the bn term and then put it in this particular formula for Parseval's. So now let's take a look at this question. Okay. The question is presented in a little bit different manner. See, nothing of this sort is mentioned, that whether you have to find the half range or a full sine cos Fourier series. Nothing is mentioned. You just have to prove that for this given function, this is the expansion. Now it is just your observation that all the terms are sine terms, there is no cos term. So automatically, and one more thing, the interval is 0 to pi, not minus pi to pi. So automatically you have to understand this is a half range and it is a half range sine series, because only the sine terms are present, cos term is not present. So automatically you have to understand this is basically half range sine series. Okay. So that means you have to use the formula of half range sine to get this deduction. Then there is a hence deduced part. In the hence deduced part, we have to show something like this. And for this part, you will require the Parseval's identity. Okay. The Parseval's identity will be required for this part. Achha. Now, Trishit, it will be only a0 square by 2, not a0 by 2 whole square. Okay, it is only in Parseval's, it is a0 square by 2, not a by 2 whole square. Okay, just a0 square by 2. Achha. So first let me do the half range sine series. So for half range sine, the calculation is quite short. For half range sine, you just have to concentrate on finding out bn, nothing else. Just finding out one integration, which is bn for half range sine. So for half range sine, this problem is usually much shorter. Okay. So I want to find the half range sine for this particular function. So my fx is x into pi minus x, and I want to find the half range sine for this. So that means I need to find out my bn value, which is going to be 2 by pi, 0 to pi, because now the range is 0 to pi, fx sine nx dx, right? So fx sine nx dx. So basically I just have to find this integration, and directly from there I should get this answer. Okay. So let's see. I will break this into two parts. 2 by pi, 0 to pi, pi x sine nx dx minus 2 by pi, 0 to pi x square sine nx dx. So basically I have to do one by parts over here. On the first part, pi is getting cancelled. Okay, so one by parts over here, 2 times by parts over here. Okay, I will use the Bernoulli formula for by parts, where I'll do the by parts directly using the formula. Okay, so those of you who are not used to using this formula, look at this part closely. Okay, this this way of doing by parts is much easier and you will avoid doing any mistakes. So what I'll do is, you first of all you just need to figure out what is the u function, what is the v function for the by parts. Obviously this x is the u function and sine nx is the v function. Okay, so what I will do is I will keep the u function as it is. Okay, always use brackets, it will be easy to do for the calculation for the next term. Always use brackets. U term multiplied with integration of v term. Okay, integration of sine nx, that is minus cos nx by n. First calculation finished. Minus, now I need to do the derivative of the first function and integration of the second function. Okay, I need to do derivative of the first function and integration of the second function, and this pattern will go on. Okay, so derivative of x, that is going to be 1, and integration of cos is basically sine, so the minus term will remain, minus sine nx by another n will come, so divided by n square. Okay, now again the same logic should continue, that I want to do the derivative of this term and the integration of this term. Okay, with a plus sign. Okay, plus minus sign will keep on changing. First you will have minus, then plus, minus, plus, like this. Now the thing is, if I do the derivative of 1, it will become 0. So that means this integration stops over here. Okay, so this integration stops over here, and I have the limit 0 to pi. I'll just directly put that. So same process I will repeat for the second integration, same process. So minus 2 by pi. I want to keep the, so this is again my u function, this is my u function, this is my v function. So I want to keep the u function as it is. I want to integrate the v function. Integration of sine is minus cos nx by n, minus, now I want to do the derivative of 2x, derivative of derivative of x square, which is 2x, and integration of the cos part, which is minus sine nx by n square. Now this will again further continue. So now the minus sign will change, it will become plus, plus minus will interchange. Now derivative of 2x, derivative of 2x is 2. Integration of this portion, integration of sine is minus cos. So already one minus is there, minus minus, it will become plus. So cos nx by n cube. Okay, and the bracket closes. If I further do another derivative of 2, that is becoming 0. So 0 to pi. Now I need to put all the limits, which I'll erase off the unnecessary part. If I put pi in place of the first function, I will have pi. I'll take the minus. There's a minus sign over here, so minus pi cos n pi by n. If I put the upper limit over here, sine n pi, it becomes 0. If I put the lower limit over here, x becomes 0. If I put the lower limit over here, again sine becomes 0. So no other terms after this. So I close the bracket. Minus 2 by pi. Again putting pi over here in the first function. So I will have minus pi square cos n pi by n. This is the first term. If I put pi over here in place of sine, it is becoming 0. If I put pi over here, then I will get another term. So the third term is going to be 2 cos n pi by n cube. Now if I put 0, if I put 0 over here, it is becoming 0. If I put 0 over here, it is becoming 0. If I put 0 over here, that term is going to remain. So minus, I'm putting the lower limit for the last term. So if I put a 0, I will have 2 cos 0. Cos 0 is 1. So just n cube is going to remain. Right? So I hope we are getting something like this. Achha. Achha, I think, did I miss out anything? No, I didn't miss out. It's fine. Okay. I hope these two terms are getting cancelled. This term and this term. Because first of all, one pi will get cancelled. There's a pi square and one pi outside. The pi will get cancelled. Minus minus will become plus, and there is a minus over here. So these two terms are getting cancelled. So what I have is this term and this term. So I have minus 2 by pi, 2 cos n pi by n cube minus 2 by n cube. So I can take a 2 by n cube common. So I will have minus 4. So let me put this minus inside. Let me put the minus inside. So 4 by n cube. I'll have 1 minus cos n pi. Okay. So now it is a good observation that cos n pi value is minus 1 to the power n. Cos n pi value is minus 1 to the power n. Okay. So that means the values over here are going to be minus 1 plus 1, minus 1 plus 1. Okay, like that, minus 1 plus 1, it's going to alternate. So when it is plus 1, this is becoming 0. When it is minus 1, it is becoming 2. Again minus 1 0, again plus 1 0, minus 1 2. Okay, so basically I can say that whenever n value is odd, cos n pi value is minus 1. So this is becoming 2. So that means I will have 8 by n cube. So there is one pi outside. I missed the pi. There is one pi outside. So 8 by n cube pi. Whenever n is odd and whenever n is even number, this is becoming 0. So 0 whenever n is even. Okay, if I express it like this, it will be easier for the further calculation. So I've got my Bn value. So I should write my final Fourier series. That therefore, the Fourier series expansion is for half range sine. This was the formula for half range sine, summation Bn sine n pi x by t. Here t is pi. Okay. Summation n equals to 1 to infinity Bn sine nx. So I'll just put the Bn value over here. Excuse me. So it's going to be acha. Now one more thing, Bn value is this when n is odd and this when n is even. So I need to interchange all the values one by one. So let me write it explicitly. I will have basically b1 sine x plus b2 sine 2x plus b3 sine 3x. Like this it goes on. Okay, and b1 value is when n is 1, it is 8 by pi. So 8 by pi sine x. When n is 2, it is becoming 0. When n is 3, this is basically 3 cube, right? So I will have 8 by pi into 3 cube sine 3x and so on. Okay, so this is my fx. So if I further simplify this, I can take 8 by pi common and I will have sine x plus sine 3x by 3 cube plus sine 5x by 5 cube plus dot dot dot. And this was the required Fourier series proof. Okay. Tell me, so is it clear up till this much? Come on, Okay, tell me some yes, no. I am getting tired from problem solving. Give me some yes, no. Come on, be a little bit enthusiastic, people. I need some enthusiasm from you transferred into me because I am getting tired. Okay. All right, great. So now finally we are stuck with the last part, which is the Parseval's identity. Okay. So going back to the question, so our first part is completed. Now the hence deduced part, which is going to come from Parseval's identity. So here one more thing, how will you understand that Parseval's identity is to be used? Usually it is mentioned in the question that use Parseval's identity. Sometimes it may not be mentioned. There is one fallacy over here, not fallacy I should say, like there is one small trick over here. When n value is at least more than 2, remember this, when n value is more than 2 in this summation portion, if, or forget about the n value, sometimes the n may not be present, better to look at the pi value. Okay, if the pi power is exactly 2 or less than 2, you cannot use Parseval's identity to get that answer, because because the function is becoming a whole square. The moment the function is becoming whole square, the pi value will be definitely, pi power will be definitely more than 2. Okay, this is one observation. If you look at all the Parseval's identity sum, you will understand. Since because of this whole square, the effect of this whole square is that the power of pi will be more than 2. So if it is 2 or less, then it is definitely not a Parseval's identity question. Then that means whatever answer you have got in the Fourier series, you need to put some value of x. Let's say x equals to pi by 4, etc., etc. You need to put some value to get that particular proof. But if the pi power is more than 2, let's say 4, 6, like this, if you have higher powers of pi, you have to understand it is definitely coming from Parseval's. In that case, if you put some value of x in the previous line, you will never get that answer. Okay, to get that answer, you have to use Parseval's. Okay. So coming to this proof, for that, what are the things I need? I need the bn whole square. I already have found out bn. So bn whole square, I already have it. Fx is provided in the question, so fx whole square also I have it. So I just need to plug in the two values on left hand side, right hand side, and get the required proof. Okay, so I'm going into that. So from Parseval's I will have, since it is half range, so the 2 will be multiplied, 2 by pi 0 to pi fx whole square dx is equals summation n equals 1 to infinity bn square. Right, this is my Parseval's formula for half range sine series. Acha. So I'm plugging in all the values, 0 to pi. My fx function was x into pi minus x. This was my fx function, x into pi minus x. So x into pi minus x, it's becoming a whole square dx. Achha, bn value, I need the bn value. This was my basically the simplest form of my bn value. This was the simplest form, but remember, this bn value corresponds only for n as odd number, not even number. Remember, you need to remember this and implement it in the answer, otherwise it will be wrong. Okay, like don't put any even value of n over here, it will become wrong. So 8 by pi n cube, where n is odd. So be careful to write down that n is odd. Don't write n1 to infinity, otherwise n2, n value 2, n value 4, all these things will come in and it will make one error. So better to write n is odd. In that case, the bn value is 8 by pi n cube. Okay, 8 by pi n cube, and there is a whole square over here. Okay, so now I just need to calculate the two sides. 2 by pi 0 to pi. If I break the whole square, it is becoming pi x square plus x square x cube minus 2 pi x square dx and over here I'll bring the constants outside. 64 by pi square I'll bring outside, and I will have summation 1 by n to the power 6. N is odd. Okay, so this is becoming 2 by pi x cube by 3 x 4 by 4, 2 pi x cube by 3, um, 0 to pi, 64 by pi square. I want to break the summation. Now be very clear about one thing, that in the question here n is 1 to infinity. That means the even numbers are also included over here. So even values of n are included in this summation, but in my expression the even values are not included. So I have to do some adjustment over here. Okay, so it is better I will expand the summation. I will write down all the odd terms one by one. So when n is 1, I will have 1 by 1 to the power 6, 1 by 3 to the power 6, 1 by 5 to the power 6, and so on. So I don't have all the terms, I have only the odd terms. Okay, and now here I need to do some simplification. 2 by pi, if I put the value of pi, it's becoming pi to the power 4 by 3 plus pi to the power 4 by 4, um, plus 2 pi to the power 4 by 3. If I put 0, everything is becoming 0. I'm bringing this term on the left side. Pi square by 64 equals 1 by, or simply I'll write 1 plus 1 by 3 to the power 6 plus 1 by 5 to the power 6 plus so on. Okay, so I need to simplify this part. I'll just use my calculator over here. The fractions are 1 upon 3 plus 1 upon 4. I think this was a minus sign. This was a minus sign. I made it a plus. Minus 2 upon 3. So that's, I guess, 1 upon. So did I do my calculations right? Let me just check it once. Someone please tell me if I have done any mistake in any calculation over here. X square. This should have been a pi square, right? I have done some mistake in the whole square expansion. It should have been a pi square, x square, plus this is going to be x square into x cube minus 2 pi x into x. Okay, so x to the power 3 by 3. So did I write the function properly? X into pi minus x. Okay. Pi square x square minus 2 pi. Sorry. I'm making a mistake in the multiplication. This is a x inside a whole square. I just missed the whole square. Okay, so better I should write it this way. I'm making a mistake otherwise. It is x square into this thing whole square. Okay, so I was missing out one power. So this is basically pi square into x square. This is x square into x square, which is x to the power 4. Then I have a minus 2 pi x multiplied with the x square. So this is x cube. Okay, so I was lagging behind one power. So it will be x cube. So this is going to be x cube by 3. This is going to be x to the power 5 upon 5. This is going to be x to the power 4 upon 4. Okay, x to the power 4 upon 4. Acha. So that means this is all changing. This is becoming pi to the power 5 by 3, plus pi to the power 5 by 5 minus 1, 2 is getting cancelled, pi to the power 5 by 2. So I hope now it is correct. Let me now check. 1 upon 3 plus 1 upon 5 minus 1 upon 2. Okay, so it's 1 upon 30. I think that is correct now. So 2 by pi into 1 upon 30 into pi square. There is a pi to the power 5. pi to the power 5 upon 30 by pi square by 64 equals this entire series, which is 1 by h. I'll do one thing over here. Now I will adjust my right hand side. Look how I'm going to adjust that. 1 plus I have a 1 by 3 to the power 6, then I have a 1 by 5 to the power 6, and so on. Okay, so what I'm doing, I'm adding some dummy terms over here, the terms which are specifically missing. I'm adding the 1 by 2 to the power 6, I'm adding the 1 by 4 to the power 6, I'm adding the missing terms. So whatever missing terms I have added, I am subtracting that to balance the everything. Okay, so whatever extra terms I have added, I have subtracted it to balance it out. Okay, Acha. So now over here, if I do some cancelling out, 32, so this is going to become 32 into 30, that's 960. So this is 1 pi is getting cancelled, so pi to the power 6 by 960 equals, now this entire thing, this is basically my required summation which has all the terms. So I can write this summation n equals 1 to infinity 1 by n to the power 6, and now this term is remaining. Now from here, if I take 1 by 2 to the power 6 common from each of the terms, okay, so this term will have 1 by 1 to the power 6 remaining. This term will have 1 by 2 to the power 6. The next one will have 1 by 3 to the power 6, and so on. So basically, again, I get back my required summation. Okay. So 2 to the power 6, and that is 64. So pi to the power 6 by 960 equals summation n equals to 1 to infinity 1 by n to the power 6 minus 1 by 64 times, if I write this in terms of summation, n equals to 1 to infinity 1 by n to the power 6, right? So if I add up or if I subtract these two terms, basically I'll have 1 minus 1 upon 64, which is 63 upon 64, right? So pi by 6 by 9, pi by 6 by 960 equals 63 upon 64 summation 1 by n to the power 6, n from 1 to infinity. If I further cross multiply, so 64 by 63, 64 by 63 divided by 960, or I should write it this way simply, 64 by 960, that's 101 by 15, and that divided by 63 is 945. Okay, so if I just cross multiply the constant, I will have pi to the power 6 upon 945 equals summation n equals 1 to infinity 1 by n to the power 6, and this was my required proof of Parseval's, right? Okay, so that's the required proof, and I guess let me just check the question. So I had pi to the power 6 by 945 summation n 1 to infinity 1 by n to the power 6, and we have got that using Parseval's identity, right? So as I told you that two sums will be 1 hour, and we are exactly standing at 59 minutes. So that was quite a nice guess. So that's it. Hope this helps. I hope. I don't know how much I am hoping. Maybe I'm hoping too much, but I hope this helps. And those who did not get time to watch the live, they can watch it in the recording. I think the recording will stay in the YouTube section. I'll not delete it.